Hello, this is Jennifer Martinez, and welcome to Eigenvectors and Eigenvalues, which is what we're going to be going over today in this video. But before we go over the definition, which is below, let's look at example 1 as a motivation to what an eigenvalue or an eigenvector looks like. So example 1 says, let A be the following matrix, and they give you two vectors, u and v. And they say the image of u and v under multiplication of a by a are shown in figure 1. And they talk about AV. Let's start with v. It says, in fact, AV is just 2v. So let's look at that and see if we agree with that. So let's look at AV. So what is A? Let's write that down, A and V. And let's multiply those together. So 2 by 2 with a 2 by 1 is going to be a 2 by 1, and that'll be 6 minus 2, which is 4. And this one would be this second column. So it would be 2 plus 0. And if we notice, this is just 2 times the original v. This is 2 times the original v. If we look at the figure here to see what that looks like, so here's v. v was 2, 1. There it is right there. And then 4, 2, 1, 2, 3, 4, 2 is right there. You can see that is just 2 times it. So it says, in fact, AV is just 2v. So A, it just stretches or dilates v. So when you have that situation, 2 is called the eigenvalue. And v is called an eigenvector, which is exactly what the definition states. So let's read the definition. An eigenvector of an n by n matrix A is a non-zero vector x such that ax equals lambda x for some scalar lambda, which is exactly what we had here. And lambda is called the eigenvalue. By the way, x cannot be 0. You cannot have a 0. X has to be a non-trivial solution of this equation, and they have a little note here about that. By definition, the eigenvalue, but the eigenvalue may be 0, and we're going to see that in example 5. And they also say here, x is called an eigenvector corresponding, so we can write that, to lambda equals 2. So it's an eigenvector corresponding to lambda equals 2. Let's look at u. U is not an eigenvector. So let's check that out. So let's look at AU. Let's write that down. Let's multiply those. So you get negative 3 plus negative 2 is negative 5. And then we get negative 1 here plus 0. There's no multiple. This is not a multiple of this, and there's no scalar that would make it such. So this is not, let's go to the left a little bit, lambda u. There is no lambda that would work here. So u is not an eigenvector. So let's practice this one more time with example 2. Different matrix, different vectors. Are u and v eigenvectors of A? So let's just look at A times u. Let's do the same thing. So we're going to take A times u, multiply those out. What do you? We get 6 and negative 30, and 30 the negative 10, so we get negative 2420. And if we factor out a 4, factor out negative 4 actually, you can get a 6 and a negative 5, so it does work. So the answer is yes for you. U is an eigenvector corresponding to lambda equals negative 4. What about v? Let's look at a times v. We multiply those together, we get a -9. And this one you get 15 minus 4, 11. This one's times -3, but that doesn't work there. So this one, there is no lambda times my u. Or, right, there's no lambda at all. So, no, v is not an eigenvector. So that is that one. So let's look at another example. Example 3 asks a different type of question, or different, right? It goes backwards. It gives you that 7 is an eigenvalue for the matrix in example 2, but now I want you to find the eigenvector. So what are we going to do here? So we know that AX better equal, right? The rule is, so in our case, since lambda is 7, or 7 is an eigenvector, we would have something like that. We can solve this equation by subtracting the 7x from both sides. And then I'm going to factor out an x on the right. You can't factor out on the left, so that would not be the same. Now, when you factor that out, that's a constant 7. This is a matrix, and you have to subtract them together. So I have to put an I here to make that all work, because you could have added a 7. This is the same as 7 times I times x. The I times x doesn't change the value of x. And so then that would all work. So I'm going to put a 7i here, as I said. And now we have an equation that we can solve. To solve this equation, I'm going to first figure out what a minus 7i is. So what is a minus 7i? Well, what was our a? Well, we have to look back at example 2. Our a was probably this, 1652. Yep. Minus 7i. I, in this case, to fit this, would be a 2 by 2. So what do we get here? This 7, actually, we can change this to put the 7 here. And so that would just be 1 minus 7. This one would not change. That 0, 5 minus 0 would not change, but this would change to 2 minus 7, which is negative 5. So we end up with the equation negative 6, 6, 5, negative 5, times some x, we'll call it x1, x2, better equal 0. Well, let's make that that is a 0 vector, isn't it? Let's make that. And we can now use matrices to solve that. So again, row reduction to echelon form. I'm going to divide through by negative 6. Leave that alone. Then I'm going to multiply the first row by 5, add it to the second row. Notice how we get a non-trivial solution. And if I write this in parametric form, I know that x2 is free. And x1 is just going to equal, right, minus, it's just going to equal x2. So then if I write what x looks like, x1, x2, we know that both of those are just x2. I can take out an x2, and there it is. This right here is called the vector, and the eigenvalue it is associated with is the 7. In fact, each vector of this form is an eigenvector as long as x2 is not 0, corresponding to lambda equals 7. So there's many eigenvectors that will work. And note that lambda in general is an eigenvalue of an n by n matrix A if and only if the equation we saw up here, A minus lambda I, right, of x equals 0 has a non-trivial solution. And the solution set is going to be all the equations of this form. And that looks like the null space. We know the set of all the solutions is a null space of the matrix A minus lambda I. So therefore, this is a subspace. And they call this the eigenspace. So the definition of an eigenspace of a matrix A corresponding to lambda, our eigenvalue, is this set, which by the way is a subspace, as we said earlier, of Rn. So we proved that before. So if we look at example 3 again, our solution was x2, 1, 1, where x2 is in reals. That set of all these is the eigenspace corresponding to lambda equals 7 for the matrix. So if you go back up and look at example 2, that was the matrix, and 7 was the lambda, and the solution was the 1, 1 times some constant. If we look at a picture of this line right here is called the eigenspace for lambda equals 7. If you remember from example 2, let's go back to example 2, they found that -4 was also an eigenvalue and associated with this vector. So if you look at 6, -5, there it is, 6, -5, lambda is -4. This line right here, all those vectors, so there's more than just one, they just gave you one, is the eigenspace for the lambda equals -4. The last thing I would like to do is look at example 4, an example of a 3 by 3 matrix and what the eigenspace looks like. So here they ask for the basis, find a basis for the corresponding eigenspace, and they give you that the eigenvalue is 2. So what I would like to do, remember eigenspace is the null space, so we want to find all the solutions, the null space to this special equation, A minus lambda I. So I'm just going to look at this form, what this looks like when lambda is 2. So let's look at A minus 2I. So here's my 2I, it's a 3 by 3 now. Notice how only the diagonals change. This is 4 minus 2, 1 minus 2, 8 minus 2. Everything else is the same because it's just -1 minus 0. And now let's try to solve that equation. I'm going to add a 0 here. We notice that x2 and x3 are free. I'm just going to write this first equation down to solve for x1. And when I do that, you can see we can solve for x1 there, which is how they got this solution. So, by the way, they say at this point, 2 is indeed an eigenvalue because we did not get a trivial solution, and we can get our parametric form. And you can see the first one is 1/2 x2 plus minus 3 x3, and then we can find the other two because it's just x1, x2 and x3 are free. This is our solution. They just decided to multiply this by 2 because they could. You could have used these two. That would have been fine. This is what it looks like. It's a plane instead of a line. This is the eigenspace for lambda equals 2. And when we multiply it by A, it's just going to be a dilation, expand it.